In this video, I'm going to go over how to determine whether a reaction, that's at equilibrium is product favored or reactant favored using the acid dissociation constants, right, the Kas. So what we have right here is propanoic acid reacting with benzoate anion in equilibrium to form propanoate and benzoic acid, right? And so there's that equilibrium right there. And so what we have are the acid dissociation constants for the two acids. So for the propanoic acid, we have a constant of 1.3 times 10 to the negative 5. And then in the case of the benzoic acid, right, we have 6.4 times 10 to the negative 5. So a very quick, straightforward way to look at it, right, is you can just look at the Kas, and whichever one is higher out of the two of them is going to be the one that is going to be the stronger acid. So it's going to be the one that then, essentially protonates and pushes the equilibrium then to form the other product, right? But we can also just simply go through actually and use these constants to actually calculate what the equilibrium value in this case right here also is. So if we look at it, right, for each one of these acids, right, the Ka is the acid dissociation constant, so that has a very specific meaning, right? So what that is that it's reacting with water, right, you form H3O plus and then the conjugate base. And so in the case of the propanoic acid, right, what we have is HC3H5O2 aqueous reacting with H2O liquid to form H3O plus aqueous plus C3H5O2 anion aqueous, right? And so this right here has that K value of 1.3 times 10 to the negative 5, right? That's the Ka in this case. And so in the case of the benzoic acid, what we have is HC6 H5CO2 aqueous plus H2O liquid is in equilibrium to form H3O plus aqueous plus C6H5CO2 minus aqueous. And so that has a Ka value equal to 6.4 times 10 to the negative 5th, right? So those right there are what those Ka values are for, right? So it's for those specific acid dissociation equilibrium constants. Now, what we can do is we can use, the same approach that we would use for like Hess's law or even just normal equilibrium constants where we can flip one of them. We can see things that cancel out, right? And then we can just multiply the acid dissociation constants, right? So if we're looking at this right here and we look at the overall reaction, we have on the reactant side, right, we have the propanoic acid and then we have the benzoate as well, right? And so that tells us that the benzoate, right, the benzoic acid dissociation reaction is the one that's going to have to get flipped, right? So we're going to flip, so we're going to take this right here, right, and we're going to flip it. And so what we'll have then as our reactant now is going to be H3O plus aqueous plus C6H5CO2 minus aqueous is in equilibrium to form HC6H5 CO2 aqueous, since it's the acid form, plus H2O liquid. Right? So we flipped it right here. So that means then in this case right here, what we have to do is we're going to have to flip our equilibrium constant as well, right? So now what we have is that the K for this reaction is going to be 1 over the Ka that we had. So that will be 1 over 6.4 times 10 to the negative 5th in this case. And so looking at that, right, what that then we can then use, right, is that we can multiply this K right here with the KQ of the other reaction, right, because the H3O pluses cancel out now, the H2Os cancel out now, so we have the reaction that we're actually looking for. So the K of this reaction that we have overall, right, is going to be equal to the Ka of the HC3H5O2 over the Ka of HC6H5CO2. Right? And so we have that right there. We plug in the numbers. we have 1.3 times 10 to the negative fifth over 6.4 times 10 to the negative fifth, right? And so already right here, we can see that we're going to have a value that's lower than 1. And so if it's lower than 1, right, it's going to tell us that it's reactant favored, right? And that has to do, again, with the fact that the benzoic acid is actually the stronger acid. So 1.3 times 10 to the negative fifth divided by 6.4 times 10 to the negative fifth gives us a KQ value of 0.203, right? Just going to add one additional significant figure, right? So we have something that's less than 1, it's reactant favored, right? And that's what we predicted just from the get-go, right? By just simply looking at the KAs and seeing whichever one was stronger, right? The strongest one is then going to be the one that's, in a way overpowering the other one, right? And then pushing that equilibrium in the direction, right, of that reaction being the one that occurs. So, yep.